that researchers believe that their results are facts, but I'm not seeing that question in the literature. So I was building off this absolutely remarkable paper by Dustin Gallison that unpacks 200 years of scientific history to conclude that very often when we're talking about objectivity, we're talking about expert judgment. So I wondered if that would apply to statistical practice. The second question was whether the interpretation of regression coefficients represents an arena within which Zhiling's paradox is encountered and navigated. And the paradox is that scientific experiments cannot be interpreted in isolation. They can't be interpreted without reference to external stuff, like existing propositions, theory, and external information. Again, this is a consistent finding in the history of science, sociology of knowledge, but I've never seen the question asked about statistical practice, and often we just assume that statistics is different because it's the numbers. So the method was qualitative. I conducted 45 interviews with academics who study health equity. It's a great field for meta research because you've got a ton of disciplines answering essentially the same question. Interviewees were in 8 countries and 15 disciplines. They were very senior, which is a limitation for sure. And the interviews formed the basis of my PhD, which was focused on disciplinary differences. So this was a bit tangential. I did a pilot phase to refine the questioning, and the interview included a section on statistical practice, which is what I'm basing this study off. So the first, I haven't got time really to do this justice. I'm hoping this is coming out in December, so please find it and read it. But the big finding for me is that the level of scrutiny researchers apply to their coefficients depends on whether those coefficients were expected. It was quite delightful to have these professor-level academics say, well, yeah, if the coefficient's going in an unexpected direction, or if it's of an unexpected magnitude, then I'm going to carefully check it using an external data set or whatever. But if it's neither of those things, I'm probably not. And as a statistician, I know that this is how it goes and that analysis is iterative. But I've never seen this in a peer-reviewed paper. This is later. And that implies that Zhiling's paradox is evident, like results are being passed explicitly through the prism of someone's existing understanding. And almost nobody viewed regression outputs as being mechanically objective, straightforward representations of reality. But it diverged from reality in an interestingly varied set of ways, which I'd love to go into detail, but I can't. So coefficients were described as being an approximation to real-world relationships, as representing one piece of reality, of being a depiction of some view of reality, or of not being capable of fully describing reality. And then this, I think, raises a line of further questioning, which is like, what piece of reality? What view of reality? There's clearly there's interpretive flexibility here, which I've never seen discussed in detail regarding my statistical practice. So this is not how we write studies up, for sure, and this is not how we teach regression methods. We tend to teach them in a very technical way, focusing on the technical definition of the coefficient. But I think my small study demonstrates there's a whole ecosystem of interpretive flexibility here, which would be valuable to unpack. Thank you.
Hey, hello everyone. I'm Ren, a postgraduate researcher from China. And with our research, we want to find information-driven study design and conduct to reduce risk of bias. Sorry. Sorry. Again. Okay. So we know that internal study is very important and have rigorous study design, such as requirements and process and written method. But it's not enough to reduce the risk of bias. And we can find lots of publications evidence that we still have high risk of bias in interventional study. So we still need to find some way to solve this problem. So our objective is to find some intervention to reduce risk of bias. And we want to know the details of this information and whether it's effective or not. So we search 3 literature database and 9 literature database. And we review more than 30,000 publications and distributions. And we exclude observational study because we want some evidence from practice, some real example. And in the end, we only have 2 information. It's very real. And the first one, I think a lot of people know that it's an independent clinical evidence committee, and also it's known as endpoint committee. It's in an RCT of the spine surgical treatment, and it reviews in outcome measurement. This study, they analyze the decision made by CEC and the decision made by researchers, and we found that CEC really classified more than 36% of adverse events in control group and about 38% in intervention group. And more importantly, CEC is more likely to increase the level of adverse events and more frequently to reclassify adverse events reported by stakeholders, because there are lots of researchers, they have some relation with company, some pharmacy company, and we know that a study funded by pharmacy company or some business company, they have more likely to have positive results. The other one is very interesting. It's a recruitment protocol. Yeah. It has two parts. The first part is if you want RCT, you need to build up a recruitment master center. It's like a service team. You have some training course for researchers, and you need to collect information on patients, and you have some people to do information management. And after the research starts, you need to follow up the patients, and if they want to drop out, if they want to quit, you need to know why, and you need to have some interaction with them. If they drop out suddenly, you need to find them and find the reason why they quit out. It's very tricky because if you push them to go back the trial, it has some ethical problem maybe. So you need to find the balance between data and the ethical. So in this study, the dropout rate is very low in this study compared to the single study, because the author said that the single study average have more than 30% of dropout rate. But only find two examples is very rare. And why? Because our search strategy try to find risk of bias. Maybe some research they said in other words that we have more high quality of results or something else. It maybe do not use the bias. And the argument that reduced risk of bias may not be the primary outcome of their research. So we may use these studies. And there are one more problem is about if we want to test the intervention is effective or not. Maybe study within a trial is a good way because you can't get funding to test the intervention. But if you want to have treatment of cancer, it can much easier to get funding. And we find some interesting example, so I don't have time to tell you about that. And we also use some computer technology to search our results, but we don't have enough time to train the module of the AI technology because we only have 2 samples. And if we want to have the excellent module of the natural process language, we need to more than 100 publications to train the module, but we don't have enough time and resources. So that's all. Thank you very much.
Next up, we have David Borg, who's going to tell us about regression intervals being underreported in sport and exercise medicine.
Alrighty. Good afternoon. If you're slipping into a post-food coma, this definitely will get you there. Alright, so I just wanted to, before I get started, acknowledge the author list on this. The data extraction was pretty extensive, and I particularly like to thank Adrian and Franco as well for the material. So, no surprise, most fields are the same. We've seen this explosion in published meta-analyses in the last couple of decades in sports medicine, and this is likely driven by a couple of factors. One of these being the incentives that go to publishing meta-analysis study. Obviously, they're highly cited, or at least the perception is that they're relatively easy to do, and they have the potential to influence policy and practice, which is for some people important as well. It's these incentives coupled with increased accessibility to software, as well as the associated resources with them that we've seen, or at least in part seeing these large increases. So I don't know, most of you will be well aware of this, but one of the early choices that needs to be made when you're conducting a meta-analysis is what type of model should be used to combine the effect size estimates. And at least in sports medicine, in practice, there's a couple of common ones. The first is the fixed effect model, which assumes that the underlying effect size is the same in terms of the true effect size, and that any deviation from those individual studies from that vertical purple line is due to chance alone. So the second model is the random effect model, and in contrast to the fixed effect model, which assumes that underlying effect sizes will vary not due to chance, but also because of between study heterogeneity. So this can be brought about through sources such as different study designs, different exercise modalities, so cycling, running, and then also testing different athlete populations. So we expect that before doing the analysis, that you would see a different underlying effect if you test different athlete populations alone, given they have different physical and physiological capacities depending on their sport of choice. So heterogeneity should influence model choice. It should also influence how we communicate the results, however we think that that's not the case. So typical behaviour is to interpret the meta-analysis using the Borg estimate, which is the central point of the purple diamond, and the 95% confidence interval, which is obviously the width. However, the confidence interval in its calculation doesn't take into account between study heterogeneity, so then it provides an incomplete summary of the underlying heterogeneity in the meta-analysis. A more practical way to interpret the heterogeneity is via the prediction interval, which obviously from a mathematical standpoint does include heterogeneity, the underlying heterogeneity in the analysis in a way that can be useful when communicating the results. Sorry, it's a bit of a mouthful. All right, so we're interested in a couple of things. The first one was how often prediction intervals were reported when someone was using a random effect model. And then we were also interested in, perhaps more importantly, how often there was a discrepancy in terms of the conclusion of the study when the conclusion was based on, if the conclusion was based on the confidence interval rather than the prediction interval. So what I would say is that in the presence of heterogeneity, the prediction interval will be wider, and almost always wider than the confidence interval. So we used the PubMed API to look at 750 articles that we randomly sampled from a decade of highly ranked sport and exercise medicine journals. We included studies that used the random effect model, obviously, and selected one meta-analysis from each paper, because they often included multiples, to extract data from. We repeated this process using medicine as a comparator, so looking at another 750 articles from medicine, and then extracted the data listed there. So not surprisingly, we found that prediction interval reporting was pretty appalling at just below 2%. It's probably not even worth comparing it to medicine because the absolute numbers are also not great. In terms of discrepancy in results, probably more worrying, we found that the conclusions of 60% of the meta-analyses would have changed if they correctly interpreted the results based on the prediction interval. So that's particularly concerning, given that these things are potentially being used in an applied setting. And then, in general, there was considerable heterogeneity with prediction intervals 3.5, nearly 3.5 times wider than confidence intervals. Alright, so pretty bleak. Very few studies report prediction intervals. We hypothesized that this misinterpretation could mean that treatments that are either lacking evidence or potentially harmful, or at the very least creating unrealistic expectations of treatment effects are being used in practice. And there's some potential fixes, and I know Matt's in the room, so I'd love to talk to him. One of them is mandating prediction interval reporting by journals, and we think we can do this via, or at least do the checks via an automated way. Setting defaults of software to show prediction intervals and not let people turn them off, and then potentially some adjustment to the filter guidelines. Thank you.
Thank you so much, David. Our last presenter for this lightning session is online. It's Shiva Raj Mishra, who will tell us about routine exclusions in nephrology trials.
Hello, everybody. I'm loading my slides in just a few seconds. There we go. So thanks for the opportunity to present. So this is the title for my talk today. I'm talking about routine exclusion in nephrology trials, particularly focusing on Australian trials. And this is a meta-epidemiological study looking at a bunch of trial protocols. And I would like to thank the study team who are listed here and the organizers for the opportunity. Without delay, so the routine exclusion happens in a lot of trials, and a high rate of routine exclusion in clinical trials could introduce a significant challenge in generalizability of trial results to the real-world population. So as a trialist, we want our trial results to be as applicable as possible to the real-world population. And this is the overall study methodology. So we come up with a pre-specified list of exclusion criteria using some scoping reviews based on prior literature. We look through the WHO ICTRP, which is WHO's trial registry platform, which pulls through different trial register like Australia, New Zealand trial registry, clinical trials, GOV, and the numerous trial register from India, China, and elsewhere in the world. And we are particularly interested in looking at the total number of exclusion and the prevalence of exclusion. And in subsequent slides, I'll talk about how we calculate the prevalence. The source strategy that we employed in WHO ICTRP was combination of a strategy based on the thematic focus, which is nephrology trials. That's something we're interested because it's impossible to focus on all trials. So we thought, like, let's start with nephrology trials. So we are particularly interested in a randomized control trial, and the source period that we employed was anywhere from 2010 to 2023. So on the introduction side, chronic kidney disease it's a major health problem in Australia and globally, and it contributes to 20,000 deaths, and that's roughly 12% of all deaths that happen in Australia. And reducing chronic kidney disease deaths requires improved primary and secondary prevention through improved diagnosis, screening, and prevention. And some of that evidence will come through randomized control trial. And these trials we want to be generalizable to the real world population. And that's the reason why we wanted to focus on clinical trials in nephrology area. And we focused on WHO ICTRP from 2010 to 2023. And these are the list of different pre-specified exclusion criteria that we tried to map using prior literature, which are listed in the bottom of the slide, and both published in 2022 and 2023. And you can see this area is emerging. Only a recent literature is available. The pre-specified criteria are broadly divided into 7 categories, anywhere from demographic, which includes older adults, women, people of marginalized ethnicity. In geographic side, we have different people of different geographic background and location. Reproductive, we often see pregnant women and those breastfeeding are excluded from clinical trials. On the comorbidities, people who are under immunosuppressive therapy, those with cancer, those who have dementia and COPD are routinely excluded. And similarly, in the disease severity, based on frailty, severity, and expected low life expectancy, that we wanted to map. And similarly, other criteria for health services language are shown in the slide. We also map passive discretion, which is an interesting focus for our study, which is defined as any subjective exclusion based on trialist interpretation of participants being able to comply or participate in the study, and their perceived vulnerability, frailty, and instability. So we use this pre-specified criteria, and we calculated the prevalence of exclusion as the total count of trials with particular exclusion A divided by the total number of trials that is applicable for the exclusion A, and then we multiplied that by 100 to get the percentage figure out. And as I previously mentioned, this is based on prior literature. And these are the list of 152 trials that we included in this particular analysis, and 81% of the trial are sourced from ANZ-CTR, and 90% of the trials were from clinical trials, GOV, and majority of the trials were non-industry funded. And similarly, we couldn't map the phase information for nearly 70% of the trial. Let's go to the next slide. So this slide shows the different exclusion criteria that we're able to map and the prevalence of exclusion, and they are ranked based on the prevalence from the left-hand side to the right-hand side. So the category that emerges as the largest and ranked first is any exclusion based on cardiovascular complication. The pregnancy and cancer are ranked as second and third, and similarly we can see people with mental illness, those in immunosuppressive therapy, those with low expected life expectancy are similarly excluded. Roughly anywhere between 5 to 15% of the trials excluded those people. Cardiovascular disease complications, that's 40%. To summarize, pregnancy 37%, and cancer at 30%. And we also map passive exclusion. So as I previously defined what is passive exclusion, and we analyzed this based on thematic classification, and the themes are on the first column on the left-hand side, divided into 4 categories, and we directly borrowed the exact quotation of the exclusion criteria into the thematic classification. And I'm going to read out one of those from our first thematic category, which is perceived ability to comply with the study procedure. One of the trial excluded with the reason being any condition, mental, physical, that would interfere with patients' ability to comply with the study procedure. And there are hundreds of different similar exclusion criteria given for passive exclusion across 152 nephrology trials.
Sorry, Shiva, I have to stop you there because you've run out of time. Thank you, everybody, for all of your presentations.